This is from Scientific American Magazine in December of 2015, let me read it. This is our starting slide, and this is kind of the overarching thesis or theme to the thing. This is really where we're going, and what we're going to be talking about is what this slide says, and I'll point out something that I want you to watch, okay? Growing number of people think that what really matters are not things, but the relations in which those things stand. We may never know the real natures of things, but only how they are related to one another. Now a question arises: what is the reason that we can know only the relations among things and not the things themselves? And the answer seems to be, the straightforward answer is that relations are all there are. So here's our thesis. The book that this comes from is called There's Nothing There. And the thesis is that there's nothing really here. There are a lot of things that seem like they're here. They seem like they're here in a very persistent sort of way. But what science has discovered in the last 117 years is that the things that we think are here are not here in the way that we think they are. And they are really only here as they are related to each other. So the operative word is relationship, the operative word is interaction. I'm going to use those two interchangeably, interaction and relationship. And I'm going to do that because science itself is doing that, is interchanging the word. They even use what I think is a Latin root of relationships, which is relata. But it's all about relationship. And what I've discovered in the last couple of years in the reading and work that I've done, not work that makes it sound like I'm in a lab someplace, reading that I've done, is that it is all about relationship. There aren't things, there are only and purely relationships. There are only purely and simply interactions. And that's the way the universe is put together. The whole is more than the sum of its parts, and I'm going to let that hang there for just a second. And that's just so important and so vital, and that's what we're talking about. All right, now, some review for those of you that have seen this before. A little bit of Albert Einstein. We won't go through his history. In 1905, Albert wrote 4 papers, all of which should have won the Nobel Prize. Only one didn't win it till 1923. They backdated it till 1921. We're not even going to talk about that one, but we'll mention it briefly next week. Didn't win any more Nobel Prizes because he was Jewish living in Germany in the 30s, and that was a bad idea. So he didn't win Nobel Prizes that he should have won. But in 1905, he wrote these 4 papers on time and space. And, well, actually, one of them was on time and space. The other 3 we will let slide for a moment. Then in 1915, his magnum opus, integrating time and space, gravity, and matter, all into one. And so what we want to do as quickly as we can is to talk about those. And it is basically the basis of special and general relativity is our starting point here. And interesting and intriguing. Now, special theory of relativity, what they discovered in the late 1800s, early 1900s is that what they thought the speed of light was a variable, that it would change under different conditions. Turns out the speed of light is not a variable. The speed of light is a constant. It's an absolute. A photon always travels at the same speed, and it travels at the speed of light, regardless. I know that you can do an experiment where you can slow light down and stop it experimentally, but I read about this yesterday. I'm ahead of you by 1 day on this, okay? And what happens is the photons are interacting with the electrons in the thing that they use to slow it down. They are still traveling at the speed of light, but the beam of light is frozen, it's stopped, it's held in place, even though the photons are still traveling at the speed of light. They're not able to escape and express themselves as a beam. Do I understand what that means? No. But I can say it, and I can get an image in my head of what's going on, is that you have to slow it down by shining light through something that has electrons. The photons interact, and there's the word again. That's the word we're going to hear over and over again. Interact with the electrons, and it makes it appear as though the beam of light has stopped, when in fact the photons are still going the same speed, but the beam in which they live has been stopped, all at the same time, okay? So Speed of light is always the same. Photons always travel the same speed. One thing that's really baffling to me that I find is really intriguing, it makes me glad I'm not a photon. They don't have any mass, so they can do this, but as soon as a photon is created, it's going the speed of light. It does not have a period of acceleration. It does not go from 0 through all of the speeds up to 300,000 kilometers per second. It goes from 0 to 300,000 kilometers per second instantaneously. There's no acceleration time. It only travels the speed of light from the time that it's created until the time that it ceases to exist. It's absorbed by something else, it's transformed into something else. If it had mass, which is why things that have mass can't do this, because they have to go through a process of acceleration. Just like when you get in a fast car or an airplane or a rocket ship, you have g-forces in a rocket ship. You're made of mass, and so you resist that acceleration. A photon has no mass, so it does not resist the acceleration. So it goes instantaneously. Photons do this, gluons do this, anything that is a massless particle traveling at the speed of light. Instantaneously speed of light. All right, so that's the speed of light. Now, the speed of light is bound up experimentally and in the universe with something else. And the relationship, there it is, you hear what I'm saying? This is the word I want you to watch for. The relationship that the speed of light has with this is intimate. They're bound together in a weird and inexplicable way, because the thing that the speed of light is bound up with is time. The speed of light is bound up with time. Now you kind of think, well, that makes sense because light travels at a certain distance per unit of time, per second, per tenth of a second, per year, light minute, whatever it happens to be. But it's vastly more interesting than that, because because the speed of light is a constant and light is bound up with time, time is not a constant. The speed of time is not instantaneous. It's not constant. It doesn't say time, simply enough, does not travel the same speed all the time. Time has a speed and it varies. That's the simplest way to say it, is that time has a speed and it varies depending upon your circumstances. Okay? The speed of time is not a constant. Time has a speed. Time changes in two significant ways. One, as you near the speed of light, and then the other one in gravitational fields. And we're going to talk about both of those. Gravitation is general theory. Speed of light is special theory. Speed of light and time. Here's a little equation. I played with the equation just to give you a sense about what's going on. Let's suppose that we could go off in spaceships and travel at these speeds. Now, you can't do this in spaceships. Some of it you can't even do in particle accelerators, but we're going to pretend mathematically that we have the technology. It's just a technological problem right now. Let's say that we could go at 90% of the speed of light, 270,000 kilometers per second. If you go out on a spaceship at 90% of the speed of light, and you are gone for 5 years, and you come back and you're 5 years older, so add 5 years to your age right now, everybody who's back here on Earth is 10 years older. All right? That's just the way that it works. That's the relationship between the speed of light and time. Time slows down the faster that you go. So if you're 20 years old, you go out for 5 years, you come back, you're 25, all of your 20-year-old friends are now 30. Okay? If you have children and you go and leave them for 5 years and you come back expecting 5-year-old children who are cute and wonderful and just about ready to go off school, instead you get 10-year-old, fifth graders who are just brats and horrible to be around. You missed all the cool years. All right. All right. Now, if you really crank up the speed to, say, this, okay, which is very, very close to the speed of light, as you can tell, faster than, well, we maybe have done this in particle accelerators in Geneva, at CERN in Geneva. If you go this fast, then things get radically different. At that speed, 10 minutes on the spaceship is 40 years on Earth. 10 years on the spaceship, 40 years on Earth. So you're 20 years old, you go away at this speed, you come back in 10 minutes, you haven't even had to go to the bathroom, okay, right? And you come back and your kids who were born when you left are now 40. They're now twice your age. Okay, so you now have jumped into the future 40 years. You jumped into the future 40 years. Put it together with the other one, you jumped into the future 45 years. And if we add, and this is the one that really fascinates me because it shows what happens when we go there, is that if you can see that the 299, 900, 2000, all those 9s and an 8, that it's essentially the same number, except way out there on the end where you got like 9998 added onto the end of it, which is about 4 millimeters. It's about this much. So you're changing your situation by this much. And at that amount of change, 20 seconds on the spaceship is 80 years on Earth. Einstein came up with this in 1905 when people were still basically riding around on donkey carts, okay? So, you know, you can't do it with donkey carts, okay? So what they did in 1971 is they took atomic clocks, because you had to have really, really accurate clocks, and B-52s, so you had to have really, really fast planes, and they put the clocks on they had two planes, went in opposite directions around the planet, and they left one on the ground, and when they came back, they were off by the predicted amount. It wasn't very much, but it didn't need to be very much. It just needed to be by the amount that was predicted by the theory, okay? When an astronaut goes into space and spends 6 months on the space station, that astronaut, he or she, will come back 0.007 seconds younger than they would have been. Okay, now that's not measurable. It's not significant in any sense. It is measurable. It's just not significant because the speeds are so slow. We don't go anywhere near the speeds that you need to do to be able to experience this. We can make particles do it in the accelerators in CERN and Fermilab and Stanford Linear Accelerator, and then we can watch the particles live longer than they ordinarily would have done. So you can actually watch it happen experimentally. So yes, verified, true, just the way that it is. Now, here's the part where it just gets entirely weird. Okay, that's weird enough. Okay, but here's where it gets entirely weird. What we're going to do is we're going to extend it to going the speed of light itself, the actual speed of light. 300,000 kilometers per second, which only, you know, massless particles can do. Photons, gluons, you know, some others. So the room is full right now of particles that are doing this. They're traveling at the speed of light. Okay, so it's not theoretical here. They're surrounding you right now. They're entering your eyeball, entering your brain, okay? They're reflecting off of everything. So we're surrounded by photons that are doing this. And they are doing this at the speed of light. 0 equals infinity, which only makes sense. The left side of the equation, things are getting smaller and smaller. The right side of the equation, things are getting bigger and bigger. We're not blasting past 300,000 kilometers per second. We're getting closer and closer and closer to it all the time. It's just that the changes are getting more and more radical the closer we get to the speed of light. The tiniest little incremental bits of increase in speed that we have, which are tiny, millions and billions and hundreds of trillions of a second, every one of those adds a radical change to the whole experimental situation until you get to the place where 0 equals infinity, and then this is the place where conceptually you have a problem because we have no idea what that means. Okay, now the federal government acts as though zero money is actually an infinite amount of money, and so that's how they spend money, okay? All right, but that's not the way that it works in real life. What this really is not that there's no time, it's not that there's infinite time, it's that all the time that there ever will be will happen in no time at all. At the speed of light, everything happens at once. For every photon in this room, its lifetime, no matter how long it is a single instant. We have sunbeams coming in, have photons that have spent 8 minutes coming from the sun. That 8 minutes for us, it's 8 minutes, for them is instantaneous. It takes no time at all. This is a fun way to say it. At the speed of light, events are not separated by time. In your experience, of course they are. That's how we live our lives, a series of events. But at the speed of light, events are not separated by time. Now, that's the first part of the special theory. Second part of the special theory, Einstein himself, he had a math professor at the ETH in Zurich. His name was Hermann Minkowski, who looked at the special theory and said, "Oh my gosh, Albert, look at this, you missed this." And Albert's like, "Oh my gosh." I mean, they did this all in Swiss German, so there you go. I could do that in Swiss German, but that would be showing off, and I don't want to do it. Minkowski and Einstein sat down, they figured this out, and Minkowski's got his name attached to it right now. The thing is that not only are the speed of light and time intertwined, space and time are intertwined. In fact, space and time are the fabric of what the universe is made of. Space and time are all woven together. We think of space and time as being separate things, but in fact what they are, and Brian Greene's got a book he wrote called The Fabric of the Cosmos, and that's what he's talking about. The fabric of the cosmos is space-time. It's inaccurate to talk about a spaceship. It's a space-time ship. You don't travel in space, you travel in space-time. You are made of space-time. Einstein, in more prosaic language, said you're just a thickened clump of space-time, kind of like a lump of cream of wheat. He didn't say that, but I'm going to say that, okay. Okay, or an unmashed potato bit, You're just a thickened clump of space-time. Everything is made of space-time. Not just space, but time. And what that means is that since space and time are woven together, whatever happens to time happens to space, which is what I want to talk about. So if I get on a spaceship, space-time ship, okay, and I'm about 6'2", and I'm traveling at 90% of the speed of light, my time is dilated by 50%, 5 years on the spaceship, 10 years on Earth. So is my space, which means instead of being 6'2", I'm 3'1". And the faster I go, the flatter I get, in the direction that the spaceship is traveling, the direction of acceleration. Okay, so if I'm standing up, the spaceship is going that way, then I reach my ideal body size. I can, I've reached bikini weight here, okay? All right. Or if I'm laying down, then I'm shorter. I'm 3'1". Relative to, not absolutely, but relative to you guys. Because it is you that I am traveling away from at 90% of the speed of light. Relative to my friends on this spaceship, we all look just the same. We are all just the same because we are not traveling at any speed relative to each other. We are only traveling at a speed relative to you. See how the relationship thing works out there? It's a relationship between us. My space-time is dilated and compressed relative to you, but not relative to the other people on the spaceship. And every speed that I go relative to anything in the universe, I'm going to have a different space-time dilation factor going on there. So it depends upon how fast I'm going relative to everything and not just the place that I left. So space and time are all related on this basically speed thing. Here's the next interesting thing when you start to think about this, because at the speed of light, what happens to time? So what happens to space at the speed of light? I'd be technically two-dimensional, but as you change directions, you realize that the two-dimension is the same in all directions. So at the speed of light, not only does everything happen at the same time, everything happens at the same place. So for a photon that has come from the sun, photon, come here. Photon, come back. I'm very impressed. You came all the way from the sun, and to me it looked like it took 8 minutes, but I hear that for you it took no time at all. And the photon says, I don't know what you're talking about. All the way from where? Right? There and here are just here. A photon is always here. He is never there. There is no there for photons. And it is always now. There is no past and there is no future for photons. And there are a lot more of them than there are of you. Which means that the universe really is much more like the way that photons experience, which means that everything happens at the same time in the same place. There's no time and there are no places. And where you live is a little bit delusional. This is the math of the general theory, the general theory of relativity. It took Einstein from 1907 to 1915 to come up with this. He had to go out and learn new math. This is another form of it that's prettier, it's more elegant. Really, really difficult math, but the operative letter there is the letter G, and that stands for gravity. The general theory is all about gravity. So what I want to do quickly is to explain to you, and this is where it just gets so elegant and so beautiful, is that what gravity is, we call gravity a force. Forces have particles, and so they think that gravity has a particle called a graviton, and it creates the gravitational field. But we haven't been able to create the energies yet, and we're never going to be able to do it that way. Maybe there's some other way you can find whether or not a graviton actually exists. So we don't know if it exists, so calling it a force is premature. What gravity really is an interaction. Gravity is an interaction between matter and space-time. Space and time are warped by things made of matter. The Earth, the Moon, the Sun are all made of matter. They have mass. Mass warps space-time. It bends space-time. And many of you have heard me say this before. Think about a trampoline. You roll a bowling ball out into the middle of a trampoline, and the trampoline is bent by the bowling ball. Space-time is bent by the bowling ball. It is bent by the Earth, by the Moon, by the Sun, by anything made of matter. So it's bent by you, and it's bent by me. It's bent by anything that is made of matter. Everything has a gravitational field. You have a gravitational field. Gravity is very weak, astonishingly weak. We have no idea why it is as weak as it is. In fact, there's a theory that says that the strength of gravity bleeds off into the fifth dimension or another universe or the Temptations or the Bee Gees. Just pick your group there. But they don't know whether or not that's true. What they do know that gravity is astonishingly weak, but its reach is infinite. That sounds like theology to me in some way. The touch of gravity is very, very weak, but it is infinite in its reach. Your gravitational field reaches across the entire universe and beyond. Very, very, very tiny, but it never goes away, which I think is cool. But gravity is an interaction between space-time and matter.
So if gravity warps space-time, does it slow space-time down?
It's like I paid you to say that. Well done, Jeff. Yeah. No, time passes more slowly close to the center of gravity. So time is passing more slowly at the bottom of my feet than it is at the top of my head. And it's measurable with really good clocks. More slowly in the basement than the top of a building. And it's but not noticeable. It's 1 part in 10 to the minus 16th of a second for every meter you move away from or closer to the Earth, center of the Earth. That's our gravitational situation. It'll be different on the Sun and Jupiter and on the Moon because of different gravity going on there. So it's going to be different depending on how much mass you've got. Ours is about 1 part in 10 to the minus 16th of a second, okay, for every meter that you move away. Which means that if you start to think about this in the same sort of way we were looking at the special theory, what happens as the mass increases, you get closer and closer to the center of mass. As time is going more and more slowly, then the question is there a place where time is actually going to go to that 0 equals infinity place because of gravity? Logical question? And the answer is black holes. Black holes are the place where the mass is so intense that space-time collapses around it, and at the event horizon around a black hole is the place where it takes, from one perspective, this is maybe true, from one perspective, 0 time to enter the black hole. From the outside perspective, it takes an infinite amount of time for anything to go into the black hole. So here's what we got with gravity. It is an interaction between space and time and mass, space-time and mass. And this is just fun, but it's redefining things for us. Our sense of the universe is an orderly expanse where events happen in absolute locations is an illusion. Baseball, wine glasses, expensive smartphones, thing that slip out of your hand accelerate toward the floor because Earth's mass warps time. The warping of space plays only a minor role in these cases. And here's why we don't understand the universe. Right in this sentence, down is defined by the direction in which time passes more slowly. Down is not a space thing. Down is a time thing. You are rolling down a time slope towards the center of the Earth into a black hole. No matter what you are doing, you are rolling down a slope of time and not a slope of space. That's just poetic and weird. Yeah. All right. That's Scientific American. All right. So what does this mean for us? There we go. down. I love that we think we understand things, and we just don't. So you take flat space, and you put something into it, and it gets warped around it, okay? You take what Newton thought of as being the way space looked, which was just flat. It just sat there wasn't anything to it. But what is actually true is that Einstein's flexible space-time is the way that it actually looks. And this is just a kind of a half of it. It's not even half, because it's not just underneath, it's all around, and not all around, but all the way down into the middle. Space-time is bent by the Earth. So satellites and the moon or everything are just rolled. You know how you put a penny into that thing at the mall sometimes and it rolls around? And then eventually goes down. Well, that's what you don't want to do. But the moon and satellites and everything are just rotating around a sphere of bent space-time in a very weird and awkward sort of way. Actually, it's beautiful. It's not awkward at all. John Wheeler from Princeton, space-time tells matter how to move, matter tells space-time how to curve, and that gives us really the relationship, the interaction between them. And he is noted for this, remembered for this statement. Space-time tells matter how to move, matter tells space-time how to curve. Gravity is not a thing sitting there waiting to happen. Gravity is purely an interaction between things made of matter and space-time. And that's all it is. It is not a thing. So when, and I read questions online all the time, and you watch movies, and somebody says, how can we have artificial gravity? Well, lots of mass, and then it's not artificial. You can't have artificial gravity. You can spin a spaceship and get acceleration, and Einstein's brilliant insight was that acceleration and gravity were the same thing. They operated the same way mathematically and physically. So it feels like gravity by spinning a spaceship. But when you go to watch Star Wars and they're in a flat spaceship and they're just standing there, that's just bad physics. Okay? It's not big enough for there to be enough mass, for there to be gravity, enough gravity to hold them onto the floor. So but you know, it's fun, so who cares? I got a couple of cool pictures that I haven't shown before. I don't know if you can see this very well. This is the Earth and the Sun rotating around each other. I don't know if you knew that the Earth had an impact on the Sun's rotation. It does. It's exaggerated here, and that's the Earth and that's the Sun. This is Jupiter. And what happens with Jupiter is that the center of, the place where the Earth and the Sun rotate around is well inside the Sun. The center that Jupiter and the Sun rotate around is outside of the Sun. They're both actually rotating, some of the time, rotating around the place that's not actually inside the Sun because Jupiter's gravity is big enough. And if you want to really think about things in a complicated sort of way, put all 8 or 9 or however many planets you want out there and try to think about all the interactions that are going on with respect to the Sun and where it's moving. And it's going to be insane. It's going to be very subtle, but it's just going to be jumping all over the place because of the gravity of the planets that are rotating around it, which I think is just absolutely fascinating. All right, here's what happened. Einstein throws the general theory out there for the world to look at. It's immediately brilliant. That was 1917. 1919, Arthur Eddington showed that it was true by using a total solar eclipse down in Principe or some island in the South Pacific. And he measured stars going behind the eclipse, and their light was supposed to be bent around the sun of those stars. So you'd be able to see them longer because as they got close to the sun, the light is going to be traveling on bent space-time, bent by the gravitational field of the sun. And he took pictures of that, and as it turns out, that's what happens. You can see a star longer behind the sun when it's an eclipse, and it reappears more quickly on the other side because its light is bent around it. So Einstein becomes world famous. General theory is sitting there, and then, as kept happening with poor Albert, something popped out that he didn't want to be there. They worked through the math of the general theory, and it was a guy named Georges Lemaitre, who was a Belgian physicist who was also a priest, which turned out to be an awkward combination. But he was a brilliant physicist, earth-shatteringly brilliant physicist, better mathematician than Einstein. He worked through the math of the general theory, and he realized that our assumption about what the way the universe was wrong, because our assumption was that the universe was static. It was just sitting there. It was infinitely large and infinitely old. It had always been there. This came out of Newtonian physics, and really the only evidence they had was that they just kind of looked at it and said, wow, looks pretty big, must be infinite, looks pretty old, must be infinitely old. and that was as far as it went. But they used that to get rid of two things. They got rid of free will and they got rid of God. And I'm not going to go through free will thing till next week. But they got rid of God at that point because they said the laws of physics make everything happen, so we don't need God to make anything happen. They didn't say God didn't exist. They just said we don't need him anymore. Scientific atheism started because we didn't need God to explain anything, the way anything happens, in an infinitely old, infinitely large universe. The whole linchpin of scientific atheism is on the idea of the universe being infinitely old and infinitely large. Then Georges Lemaitre comes along, this Belgian physicist priest guy, works through the math of general theory. He writes Einstein letters. He says, Albert, dear, holy moly, Albert, the general theory clearly implies that the universe is expanding. It's not static. It's not just sitting there. It's expanding. And then he made his own brilliant leap of logic. And he said, if it's expanding as you go forward in time, then as you go backwards in time, it's contracting. Now you can expand forever, but you can't contract forever. And so Lemaitre said it contracts all the way down to what he called a primeval atom, which he thought was about the size of the solar system or the distance between the Earth and the Sun or whatever. It doesn't really matter. It was bigger than it actually was. As the theory progressed and people started to figure it out, it contracts all the way down to a single point, the same kind of point that you have in the center of a black hole, called a singularity, an infinitely compressed point of pure energy potential with nothing in it. And he said the universe had to come from this primeval atom. Einstein said, no, I don't think so. That's not possible. The universe is infinitely large and infinitely old, and so it's not possible for it to have a starting point. That's just not on. But as time passed and the theory grabbed hold and evidence started to present itself, Einstein had to change. And the most significant evidence came from Hubble, Edwin Hubble, the astronomer, who in 1927, 28, 29, with two groups of people on Mount Palomar and Mount Wilson in California, discovered, in fact, that the universe is expanding. He found the observational evidence that what the general theory predicted was, in fact, true. Recognizing that between 1923 and 1927, the only evidence we had that the universe had a starting point was the math of the general theory, and it was so brilliant that people were compelled to start to think about it as maybe being true, just because of the math of the general theory. And then Hubble discovers in 27, 28, 29 that the universe, in fact, is expanding using something called the redshift, and you can ask me about that if you want. But what really happens is that there's two things, there are two interpretations to this information. If the universe is expanding away from us, then either we're at the center of the universe, which is possible. It's a violation of the Copernican principle, but it's possible that we are at the center of the universe, or that in fact the universe had a starting point. 1929, astronomer Edwin Hubble studied light waves from distant galaxies and concluded that the universe is continuously expanding in all directions. This work was part of the basis for the Big Bang theory, the idea that the expansion began from a single point with a huge explosion. That's really, really good physics in a comic strip, except for the word explosion. It was not an explosion, it was a super rapid and continuing expansion, that the universe expanded from a single point and became the universe. We should finish the cartoon. Why is it the universe keeps expanding but there's never any room in my closet? The universe is expanding between galaxies and not inside of galaxies or inside of closets. So that's the answer to the cartoon. Still pretty good physics. And so we reach the Big Bang. And here's what we need to say about this, is that science did not like it. But science had to just get over it because it was true. And the reason they didn't like it is because here's what they said, and here's what we need to understand about Big Bang. You don't really understand about Big Bang initially because you hear it, you're not really it's fun to go up and ask somebody who doesn't know and say, please explain Big Bang to me, tell me what you think it is. And the answers will be fascinating. But what it really is that all of space and all of time were collapsed into the singularity, which means there was no space and there was no time. Space and time were not sitting there waiting for something to happen. Space and time came into being. No vacuum, no emptiness, no universe, no energy, no particles, no gas, no laws, nothing. Everything came from nothing. There was no where there for the singularity to be therein. There was no when then for it to be then in. Space and time did not exist. There was no pre-existing space for the singularity to be in, to expand into. Space didn't exist yet. And your brain right now is going, ah! Okay, because it doesn't, that's the place where we go conceptually that we can't go conceptually. All of a sudden, our brain doesn't know how to do nothing because we are trapped conceptually in a four-dimensional construct. We naively and innocently and sweetly assume that a four-dimensional construct has always been and will always be. In fact, this four-dimensional construct is a created thing that happened in a scientifically describable, mathematically describable sort of way. And it happened very, very quickly. It went from nothing to the size of a universe. Well, inflationary theory tells us that in a trillionth of a trillionth of a trillionth of a second, the universe went from the size of a proton to 250 million light years across. In a trillionth of a trillionth of a trillionth of a second. As close to being an instantaneous appearance of an entire cosmos full of space and time as you could possibly imagine. But look at this is from CERN's website in Geneva. Look on the end over there. Can you see what it says? I don't know if you can see it from the back. Time begins. It says time begins. Time and space begin. That's a phenomenal thing to have on a website of one of the world's most respected science institutions, and it would not be there if that were not what we believe to be the case. Time and space began. I like that cartoon. Einstein's universe looks like this. The universe is not infinite in space and time. They both had starting points, place where they each began about 13.8 billion years ago. The singularity, there was no space, there was no time, there was no matter, there was no energy, there was nothing of any substance. There were no laws of physics. The laws of physics happened inside the universe. The universe produced the laws of physics. The laws of physics did not produce the universe. Think about that. There was nothing. There was nothing.